now we have the 6th lecture on the module 2. In this lecture we will talk about the dynamics of one of the type of structure which is articulated towers. We already discussed the dynamic analysis of fixed jacket structures. We have also seen how to handle the wave loads using the nonlinear drag part by linearizing it. We have also seen how to handle the earthquake forces for two type of system. One is let us say founded on seabed or resting on seabed. Conceptually we have of course derived the equation of motion for this, whereas for the system which is compliant we have discussed the concept. In the coming example we will show you how this can be analyzed using the convention theory for a compliant system. So, in this lecture we will take up one articulated tower. We have seen in the last lecture what are the application advantage of articulated tower, where they have been used. In this lecture we will talk about the dynamic analysis of this. Of course, we will show some results of the dynamic analysis and some of the important conclusions for this kind of compliant tower in this lecture. So, if you look at the mathematical model, we make certain assumptions that the fractional deformation of the tower are negligible compared to its displacement of the rigid body. That is very important, because now we idealize this tower as a rigid body motion. So, the fractional deformations related from the tower members because of the lateral loading acting on the tower becomes negligible. They of course exist, but they are very less in magnitude in comparison to the displacement of the tower as a rigid body. Therefore, the tower is idealized as a single column undergoing motion only in the plane of fluid caused by the waves. The base of the tower is considered to be a hinged joint, it cannot take any moment. The tower is discretized into number of segments and the mass is lumped at appropriate nodes. So, what we do is we pick up a tower, we see in the left hand side here, and you can see there are discretized points which has been dividing this tower into various components. So, the height of the tower, the physical dimension is about 275 meters, and then the buoyancy tank is about 70 meter deep, which is located close to MSL or the still water level, and of course, a free surface or the free board at which the deck is placed with respect to the still water level is about 50 meters, and the deck is having all conventional directional arrangements which is not shown in this figure, but that will attract the aerodynamic loading on the structure. So, the equation what you see here is the equation of motion. So, we write the equation of motion back again here, then I will explain each term of this equation of motion in detail. Let me call this equation number 1. Now, in this equation K is the rotational stiffness. The degree of freedom for this problem is theta, that is the base rotation at the hinge here. The degree of freedom is the rotation of this hinge here, theta. That is why the equation of motion is written in theta double dot, theta dot and theta. K is the rotational stiffness, is nothing but the moment required to cause unit rotation. Stiffness is the force required to cause unit displacement. Similarly, here it is rotational stiffness, therefore, we say it is the moment caused or required to cause unit rotation at the base of the angle or base of the hinge. when the tower is in undisplaced position. So, you can easily find out k by this conventional method, and of course, omega here you see is of course the natural frequency of the tower, which is square root of k by I naught in radians per second, and I naught is the mass moment of inertia, of the tower about the hinge when theta is 0, that is at undisplaced position as you see in the figure here. That is why it is called I 0. I naught is the mass moment of inertia of the tower about the hinge when theta is 0. I naught beta of t is the added mass term, is the time varying added mass moment of inertia, I will come to that how to compute this. It is time varying added mass moment of inertia, whereas k nu t is again a time varying rotational stiffness. So, time varying rotational stiffness this depends on the number of submerged elements at any instant of time, whereas k is the rotational stiffness at undisplaced position. So, I think you will understand that now. When I apply a lateral force to this tower, when I have a tower this form, a single tower hinged at the bottom subjected to wave action, there is a lateral force, of course there are derricks etc., and there is a wind load acting, we will come to that figure conceptually later. So, when I try to apply the lateral force to this tower, the tower will have a tendency to rotate. So, I call this as theta. So, when and there is a buoyancy chamber here, there is a buoyancy chamber here. Now, depending upon the number of elements which is submerged, you work out k nu of t, which will be the time varying rotational component of the stiffness. So, that is why you have two terms here, k theta and k nu of t of theta. Similarly, you have two terms here, I naught theta double dot, which is conventional mass moment of inertia when the tower is at undisplaced position when theta is 0, and I naught beta theta beta t of theta double dot, which will be the time varying added mass moment of inertia, because during any instant of time you will see the submerged elements will have a different volume of submergence that will attract more mass moment of inertia. All these moment of inertia are computed about the base here. Okay. And of course, f of t is a time varying vector, time varying load vector, which in this case arise from wind and waves, both are considered in this analysis. And in this case essentially f of t will be the moments caused by these forces about hinge, not the load actually, it is the moment. that is the moment caused by these forces about this hinge. So, let me rewrite this equation again here. Let us say I naught I call this equation number 1. I rearrange these terms, simply I say rearranging I naught theta double dot plus 2 zeta omega I 0 theta dot plus k theta as f of t minus k nu of t theta minus I naught beta of t theta double dot. Call this equation number 2. Now, I want to find I naught beta t k and nu of t for equation 2. That is my objective now. To do that, let us draw the initial and deflector position of the tower. So, I pick up any element here which is k. I call this length of the element from the hinge as Sk, and the element has Wk as weight. Now, of course, we know that this value will be Sk sin theta. So, now from this figure, let us say the overturning moment which I call as m overturning is given by, so m overturning the overturning will be responsible for Wk and this distance about this edge. Okay. So, that is going to be sin theta of sum of Wk Sk. I have taken sin theta out, I am summing it for k equals 1 to n capital N, where Wk is the weight of the kth element in R. Sk is the distance of Cg of the kth element this is the distance of Cg of the kth element from the base measured along the tower. Of course, n is the total number of segments. You are dividing this n number of segments, total number of segments. Let me call this equation number 3. 2 was a rearranged equation of motion, and now this is the moment responsible for overturning. Now, there is a restoring moment also. I will remove this. Can I rub this, because it is difficult to move there? I will retain this figure, rub this. Is that okay? Can I remove this? Now, the restoring moment which I call is given by summation of k equals 1 to small n rho w g, because I am talking about the submerged volume now, of sin theta Sk Vk, where first of all n is the number of submerged elements, and Vk will be the volume of the kth element. Of course, rho w is the density of sea water, and theta of course the degree of freedom, where the angle of rotation at the base of the tower. So, I have got two equations now, one is the overturning moment, other is restoring moment. Making use of these two, I find the net resistive moment. Which I call as R of t is given by the restoring moment minus overturning moment, which is given by sin theta of rho wg of sum of k is equal to 1 to n Sk Vk minus sin theta of sum of k equal to 1 to n SkWk, whereas I change the subscript to n0, where I call this equation number 5, where n0 here is the total number of segments of the tower submerged in the undisplaced position. Now, we all know in the equation of motion that the restoring component is actually in the equation of motion. The restoring component is given by k times of 1 plus nu of t of theta, is it not? So, I should say that the net resisting moment r of t should be actually equal to k of 1 plus mu of t of theta. I will remove this. So, let me write that k of 1 plus mu of theta should be equal to sin theta rho wg k equals 1 to n naught sk pk minus sin theta k equal to 1 to capital N of sk wk. I call this equation number 6. So, for small rotations of theta, I can simplify this equation as k will be simply equal to rho wg k equals 1 to n naught sk vk and hence nu of t can be straight away given by r of t by k theta minus 1 from this equation. Now, what we see from here is an important observation. What we see from this equation is, let me call this equation number 7. An important observation what we see from here is the nu of t depends on time t and theta. So, it is displacement dependent. And displacement is non-linear. Therefore, there is a non-linearity here in the system. So, we wanted to find nu of t and k, we found that. Now, let us talk about I naught. I will remove this. Any questions here so far? In the equation of motion, we had some unknowns, we are deriving them one by one. I got k and I got nu t now. I will find beta of t and I of 0 from now in the second derivation. So, I will have the full equation of motion with me. I will talk about the right hand side of equation of motion f of t. I will tell you how to solve this in what scheme, then I will show you the results how it has been solved. So, I will remove this now. Any questions here? Now, I want to find the mass moment of inertia in the undisplaced position. The mass moment of inertia of the tower at undisplaced position about the base, because always we have to find the moment of inertia about a specific reference datum, we say it is the base of the tower, is simply given by I of t okay. We simply say about the base at undisplaced position, we say I naught. I naught is simply sum of k equals 1 to n, that is my number of elements or segments in the tower. It will be simply length of the member by its mass plus rho of sea water, I am using rho w, okay, rho w of the submerged elements now, k equals 1 to n naught Cm minus 1 of Sk square Vk, I write it here Sk square. So, this is the dry weight, this is the submerged weight, I am taking the volume here, multiplying with the density, and n naught is the number of submerged elements, and 0 all stands for undisplaced position. So, I get I naught, I call this equation number 8. At any instant of time I want to get beta t, which is a function of again I naught, but that is going to give me the added mass variable submergence effect at any time t. So, I must get beta t. Therefore, what would be the mass moment of inertia of the tower at any instant t, at any instant time t, which will be given by I of t, which is again k equals 1 to n Sk square Wk by g, that is the mass, plus of course rho w multiplier out, k equals 1 to n star, I will come to that what it is, Cm minus 1 Sk square Vk, where I call this equation number 9, where n0 star is number of submerged elements at any instant time t. And we already know that this IT should be equal to I naught of 1 plus beta and so on. So, from which I can find beta of t as IT by I naught minus 1, equation number 10. So, IT is instantaneous moment of inertia about the base, whereas I naught is the undisplaced position. The ratio of this minus 1 will give me beta of t directly. So, in my equation of motion I wanted I naught, I wanted beta of t, of course beta of t, I wanted nu of t, and I wanted k. I got all of them now. Any doubts here? Now, interestingly, all of them are obtained. There is an important observation here. The observation is that beta of t is also displacement dependent. How? I will come to that. It is displacement dependent because beta of t is actually depending upon I of t and I naught. I naught is at undisplaced position, so there is no problem, whereas I of t talks about number of n stars which are number of submerged elements. Okay. So beta of t is also displacement dependent, again this is non-linear. Okay. Now in the equation of motion we have left out only with one term, which is f of t, which we will now discuss. Any doubts here? We are formulating the equation of motion term by term, then we will try to give you a scheme how this has been solved. We will derive the scheme here, then we will do an iterative operation, show you the results directly and discuss the merits and demerits of these results. Of course I will not be able to show the live solution of this equation of motion here, it is a iterative scheme, it is not possible. I will show you the results directly after we complete the formulation of the problem. Now we are doing the mathematical development of the problem. Now I am focusing on f of t. Any doubt here? Let us talk about right hand side of equation of motion, which is f of t. As I said, f of t considers two components, one is the wind load. We already know how to compute the wind load, we have the governing equation with us. I will just explain schematically, I am not giving the equation because they are available in module 1. So this is my superstructure above the still water level at the reference datum of 10 meter, at the reference datum of 10 meter above the MSL, till that value the pressure is constant. After that the pressure varies, let us say some value of Z naught, then the pressure varies as a power law. Okay. I compute these pressure values at any instant of time at any point I want. Okay. So I know the pressure, from the pressure I know the force because the projected area is known to me, because I know the length of the node. How? For example, I will magnify this. I have a member, this is my ith element, this is I plus 1th element. I know the length of the element, which is j. I know the pressure here and I know the pressure here because it keep on decreasing. So I will assume this is to be linear in between this, because the length of the element is so small, I can linearize this in between this term. I can get the Cg of this, I can get the multiplier and length of this, I know the projected width of this, I get the area. For that force now, what is the distance of that Cg from the base will give me the moment, which is f of t. I can do this for n number of elements and keep on adding them. Is that clear? Any doubt here? I am not explaining this governing equation because already we have this power law given to you. We already know, I believe that you have read this and you have understood how it has been computed. This is a scheme how it has been done. So I think there is no difficulty in finding out f of t cost because of the wave load on any member and any element you want, because all these are not forces, these are moments about the base. Why we are talking about moments? Because my displacement degree of freedom is not x, it is theta. So I am talking about all moments because I am talking about rotation. Is it clear? I will remove this. The second force of course we have is the wave load. He will try to slightly expand this because I need this to expand it for understanding the scheme of solution procedure for this problem. Okay. So we already know the hydrodynamic force on the submerged portion of the element is given by, let us say, f I of t. I am using I here, I will explain what I is. Half rho CD dia of the jth element, okay, is given by jth element u dot nj, no, ni, this should be ni because that is a node ni, minus theta dot into hi, I will come to this what it is, multiplied by u ni minus theta dot hi mod value plus pi d square by 4 of the jth element Cm rho w u double dot of ni. I call this as equation number 11. 10 is here. We will quickly explain what it is, but I want to write one more equation. This is at ith node. Now, at ith node, the force per unit length is given by here. I want to write the same algorithm for I plus 1th node. I am talking about two nodes, ith node and I plus 1th node. So, the j element is between these two nodes. This is my element, this is my jth element, this is my ith node, this is my I plus 1th node, and this is my diameter of the member, the jth node. That is what I am using here. And the velocity and the displacement, I mean the angular velocity is all at I. What is hi? I will come to that. First let me write I plus 1th node. So, f of I plus 1 of t is given by, simply replace all this with I plus 1, half rho CD dia, and the dia will remain same because it is not the node, it is the member, okay, u dot n I plus 1 minus theta dot hi plus 1 mod value of plus pi d square by 4 rho w Cm u double dot ni plus 1. I call this as equation number 12. So, in these two equations, let us say the set of equations 11 and 12, I understand that I and I plus 1 are the nodes at which f of I is calculated. Dj is the diameter of the jth element lying between I and I plus 1 nodes. I will rub this part. Of course, rho w is density of seawater, CD and Cm are the drag and inertia coefficients, we know them, and u dots are the water particle velocities at ith and I plus 1th nodes, which are calculated from appropriate theory. Theta dot is the angular velocity at ith and I plus 1th node of the tower, which is my displacement degree of freedom. Hi or hi plus 1 is the height, I should say distance, of the ith or I plus 1th node above the base. Which is the base? Hinge. Hinge is my base. Now, you may wonder that why I am multiplying this with theta dot. Importantly, remember I am looking for the moment of these forces. Okay, so that is why I am multiplying it here. Hence, the hydrodynamic force of jth element and moment caused by this force about the base is computed for jth element. If you want to do it for the entire tower, I should keep on adding this for different number of elements. So, now my f of t comprising of wave and wind are clearly known to me. I know how to divide them in segments, the superstructure part above the still water level, find the aerodynamic forces and the corresponding moments of these forces about the base of the tower. For the hydrodynamic part, I will again subdivide into different number of nodes, the portion below the still water level, and find out water particle velocity at the respective nodes and the distances of those nodes from the base. Keep on adding them, I will get the moments. So, f of t can be easily obtained for the entire tower, which comprises of lateral loading caused from hydrodynamic and aerodynamic. Now, the interesting part here is there is an observation. K nu of t beta of t and f of t of course are non-linear. I have already shown you how k, nu of t and beta of t are non-linear. I think you will very well appreciate why f of t is non-linear, because of the drag term present in the hydrodynamic forces. You also have non-linearity from the drag term present in the aerodynamic forces, because if you see as a v square, they are also in pressure drag in aerodynamic forces. So, there is a drag term present in aerodynamic as well as aerodynamic forces, therefore, f of t is also non-linear. When you have any of the system non-linearity of this order present in any given dynamic system, can you solve this by any methods? There are three methods available. One is what we call time domain method, other is frequency domain, other is iterative frequency domain. So, I will solve this problem now with a new algorithm called IFD, that is iterative frequency domain. I will pick up this problem in frequency domain and iterate it in frequency domain and solve. It is a new algorithm, which is a research based technique, which is very commonly not applied for offshore structures. Okay. There is an advantage why I pick up iterative frequency domain to solve this problem. I will show you at the end once I do this problem. So, what I will do here is, at one iteration I will show you the control equations. Okay. You have got to iterate that, write a program, iterate that and get the solution. Once we understand the control equations at one iteration, then we will directly show you the results on the screen here and we will draw the inferences from the results. That is what I can do as far as the classroom work is concerned. If you have any difficulty in formulation of the problem till here, please let me know how we have formulated the whole problem. We started with an idealized tower model like this. We picked up the degree of freedom as rotation at the base. This is one of the approaches. We subdivided the tower and the deck, of course, at different number of nodes, and we found out or wrote the equation of motion, rearranged them, and then we found out each and every term separately. Then we understand hypothetically and mathematically how to compute the equation of motion or f of t at any node I want or any member I want. Okay. Now, I am looking for a scheme to solve this equation of motion. The solution of this equation of motion should give me the displacement degrees of freedom, which is nothing but theta for this problem, is it not? That is my solution, right. I must get theta as a time history or as a power spectral density function if I do it in a frequency domain. Okay. So, time is not there now because this will take another 1 hour. So, already we had enough equations written on the blackboard today. So, I will not load you further because I have got around, now we have finished equation number 12. So, I have total around 36 equations. So, it will take time. So I cannot do it, I do not want to hurry up because 10:46 now. We will stop it here. If you have any questions, I think we can spend couple of minutes in explaining you those answers if it is quickly possible. If you have no questions at all, I think I am very happy that in one instance I are able to understand the analysis. I am really, I think there is a magic happening. So there may be a large amount of audience which may feel that okay sir, as long as you are writing on the board, as long as we see it on the screen, as long as you are promising us the results, we have absolutely no problem at all, because we agree whatever you say. The results are fine, equation of motion is agreed, because I see some 2 zeta omega terms there, I understand Cc as a ratio. So all these are appreciable, I am able to get those ideas, and you have explained some complex terms as beta of t, nu of t in the derivation here, though I have not understood completely, but still I will try to understand them, but I think they are here with me, I can always read it. So iterative frequency domain is a very interesting solution scheme, it is a new, it is conventionally not done in dynamics of ocean structures. So it is a new scheme, it will take some time for us to understand, we will go slowly in the next lecture, possibly on Monday morning. So you will be also remaining fresh at 8 o'clock, so we will load you with more equations and understand the scheme, and I will write a control equation for one iteration for the whole scheme. Then of course we understand that you will write a program for this and try to solve this problem. Of course I will give the data for this problem, it is available here, that is the data which I am going to use, which is taken from this specific paper. So this is what you are going to use, so all the data are available with me, I will solve this equation of motion and I will give you the results directly, that is the idea. So any questions? Not
as the outcome of the dynamic analysis.
That is interesting question, that we of course when we solve this equation of motion, the variable in the equation of motion I think we agree is theta, which is the displacement degree, in this case is rotation. So either I must get the time history of theta of t, for any instant of time what will be the rotation of the base at the hinge I can find, or if you do a frequency domain analysis I will get power spectral density function for a wide range of frequency of theta. Now from theta, since you know the tower dimension, I can always find x, which is nothing but the tower length multiplied by the sine angle of that, I can always find. I can find the maximum displacement of the tower, I can find the settlement of the tower if it happens, and so on, if I know theta. I will check whether the maximum displacement is beyond the permissible value, is it running in kilometers, and so on. From this I can easily connect this to my stability of the model also, which I am not touching here, can be done. So the outcome of this equation of motion, or the solution of the equation of motion to be precise, will be time history of the rotational degree of freedom or power spectral density function of theta. But of course in my procedure I will get PSDF, because I am doing it in frequency domain. I am calling this iterative frequency because I will show you how I am iterating. So it is IFD, it is not time domain, it is iterative frequency domain. So that is what it is. So we will get theta, right. Of course using Fourier transforms you can get PSDF converted to theta of t also, I will not show that here, I will directly look at PSDF of thetas. Okay, so it is a simple idealized problem, that is why I picked up this example for us to understand how I can do dynamic analysis for a AT. Of course I will extend this for multi-legged articular tower in the next successive lecture. There I will talk about not the solution procedure, talk about control mechanism of MLATs. How do you control the response, because I know how to get the response, now I am interested in controlling them. So what mechanism do I do? I will use tuner mass dampers, I will give a secondary system of dynamic vibration, control the response of the tower. That is what I will discuss in the next part of this problem, after I complete the results of this problem. That is about AT. So the third class of problem will be a TLP, the fourth will be a new generation offshore structure which will be a triceratops. Again we will derive the mass stiffness matrices completely here, we will not solve it here, we will solve solution, leave it to you, but you can refer the journal papers to understand them. We will discuss only the summary of results. So that will end the second module completely. So first module spoke about basics, second module is speaking about applications, third module will talk about advanced applications in stochastic dynamics. okay that is what the plan is. So any doubt except one, anybody else? Okay.